This video is on Unit 7, Chapter 14 on regression, Lesson number 2, Quadratic Regression. In Lesson number 1, we looked at scatter plots and you were introduced to linear regression. In this lesson, we're going to focus on quadratic regression, which just simply means that the data that we're going to be looking at is going to create a quadratic relationship. So looking at your notes here, linear regression is used to write a line of best fit equation for data that follows a linear pattern. Sometimes data follows a curve, and it's more appropriate to write a curve of best fit equation using quadratic regression. The coefficient of determination, which is r squared, indicates how well the data fits the equation. It is a number between 0 and 1. The closer to 1, the stronger the data. The closer to 0, the weaker the data. So again, 0 is going to indicate more of a no correlation between the two things that you're comparing, whereas the coefficient of determination being a 1 means that there is a strong correlation in that data. Now remember, R is associated with linear. So when we talk about correlation coefficient, which is just plain R, that's linear in nature. But your coefficient of determination is the r squared calculator is going to spit out. The r squared we use for any curves of regression. So anything that has a curve in it, quadratic, cubic, quartic, exponential, things like that. So the steps for working these is exactly the same for quadratic as it was for linear, with the difference of we have to choose quadratic regression um, when we go to create that equation. So you're still going to enter your data, hitting stat, edit. X's are still going to go in L1, Y's are still going to go in L2. And then to actually find the equation, you're going to hit stat, arrow over to calc, select number 5, and then hit enter. I would like to remind you that we store the regression equation in Y1 by going to store regression, alpha, window, I think, or alpha trace. We'll look at that as we get through an example. So question number 1 says, an amusement park ride takes riders to the top of the tower and drops them. Table below shows the height and feet of the riders at various seconds after it drops. We're going to put this information into L1 and L2 because time is your X, height is your Y. So going to stat, oops, not that. We're going to go to stat, edit. Now I have information, just as a reminder, if you arrow up, all the way up so that the L1 or L2 is highlighted, hit clear and then enter or down, arrow up, clear down, it clears out that information. So I'm going to put my X's in, I got the 0, 0.5, 1, 1.5, and the 2, arrow over for the Y, 100, 164, 120, 68, and 8. So I would like to show you something in the graphic calculator before I move on to trying to answer these questions. If I hit zoom and then stat is number 9, if you look on my window here, zoom stat is number 9. I'm going to hit number 9. What it does for you is it changes the window on the calculator so that you can see the data that you just entered. Now it's hard to see, but there is a small curve to this, creating a quadratic regression. I'm going to go back to stat. I'm going to arrow over to calc. Now we need to select number 5, which is quadratic regression. I'm going to hit enter, 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 alpha trace, enter, enter, enter. Now, just like we did in lesson number 1, you'll notice here on this screen, it gives you the generic form of quadratic regression equation, y equals ax squared plus bx plus c. And then it proceeds to give you the a, the b, and the c to write the equation. Also, I would like to point out your r squared is equal to 1. So there is a perfect relationship between the time in seconds and the height in feet that the amusement park ride takes riders on. I'm going to write my equation. I'm going to go back to my worksheet. Part A says write an equation for the curve of f(x). We got y equals negative 16 x squared minus 4x plus 200. Part B says state the coefficient of determination and explain the significance. So the coefficient of determination is 1, which means that our data has a very strong correlation, or if you want to say relationship, that works as well. Part C says how many seconds will it take an hour to reach the ground. So think back to when we did projectile motion. So when things hit the ground, I'm going to look at the graph here. When things hit the ground, that would be a 0 here, right? So where it hits the x-axis is a 0. So we can do a couple of things. We can go to the table of order pairs, see if we can see where the y value is 0, which we can't. So I'm going to go to second trace, and I'm going to do number 2, which is a 0. Now, what I'm going to do here is I want you to do something a little different than what I taught you in that lesson. I want you to try to put the cursor on the x-axis. Now, what that means is y value would be 0. Now, that's pretty close, but we need to do a left bound. So I'm going to hit the left arrow key about 4 or 5 times. I'm going to hit enter. And then I'm going to hit the right arrow key, go back to where I think the 0 is, and I'm going to hit the right arrow key about 4 or 5 times and hit enter. And then I'm going to hit enter one more time. So at 2.06 seconds, at 2.06 seconds, the tower is going to reach the ground. Let's look at number, I'm going to jump over to number 6. And the reason why I want to talk to you about number 6 is because the data here is given to you in terms of years. When we put these things into the calculator, typically we don't use years in the calculations. What we do is we say, well, whatever the first year is, that's going to be year 0. The 2005 is going to be year 0, which means 2006 is 1 year later. So 2006 is going to be year 1, 2007 is going to be year 2, 2008 is going to be year 3, and so on for this data. So when we go to put this in the calculator, we're going to go back to stat. First of all, I'm going to clear out my equation. I'm going to go to my stat edit, clear out this data, and I'm going to start putting in the x's, which is 0, 1, 2, 3, 4, and 5 for my y values. Got 158, 145, 132, 130, 138, and 142. And I will remind you one more time that it is a good practice to get into checking to make sure that you have entered all of the data correctly before you move forward. If one of those numbers is wrong, everything from this point forward is wrong. Going back to the worksheet, it says the data below shows the average sale price of a house in Norfolk, Virginia in thousands of dollars during certain years since 2005. Part A says write a quadratic regression equation. So let's go back to our calculator and let's go back to stat, calc. Number 5 is quadratic. Enter, enter, enter. Alpha trace. Nope. I don't know what button I just pushed, but we're going to do that again. So I'm on um, our second trace. No, let me go back to my stats. Edit. I've got the information in there. So now I'm going to go back to stats, arrow over to calc. Number 5 is quadratic. Enter, enter, enter. Alpha trace. Enter, enter, enter. All right, so here is our equation. Again, the generic ax squared plus bx plus c. Your a is 3.018, and your b is negative 8.032, and your c is 158.25. So let's create our equation there. Y equals 3.018x squared minus 18.032x plus 158.25. So there's the equation. Predict the value of the house in 2015. Well, here's the question. In 2015, um, what year is that? So if I take 2015 minus 2005, that would be year 10 if I were looking at my table of ordered pairs. So my equation did end up in y equals. You can zoom 9 to look at the graph, and then second trace is going to take us to the table of ordered pairs. And if I look at year 10, which is the X, I've got approximately 279.71 thousand. So let's just say that that's 280,000 approximately. Now, the reason why I did not keep decimals here is because I'm making my answer match the way that it looks in the table. Part C says predict the year the average sale price will exceed 200,000. Well, if we look at our table of order pairs here, the year that it exceeds 200,000, so in year 7, at the end of year 7, that's how that's spread. At the end of year 7, house prices for 179,900. In year 8, the end of year 8, it's 207,000. So somewhere in the 8th year, house prices exceeded 200,000. So in year 8. So what year would that be? Well, 2005 plus 8 is going to be 2013. So that's the year. Part D says compare the data in a given table to the table provided by the regression equation. Why are the values for the same year? So let's look at year 2, for example. Year 2, according to my table, says 132,000. Year 2 on my table of repairs is 134,000. So the biggest difference that you have here is that the regression equation is a prediction. It's not exact, especially when we look at the graph. If you go back and look at the graph, so the curve that you actually see here is the regression equation that we came up with, or the calculator created from the data. You'll notice that a lot of your data points don't even hit the curve. So the data points are not going to fit exactly on that curve because, again, it's just a prediction equation. It's not going to fit the data exactly. Um, so there are your notes for lesson number 2 in chapter 14.